Hello, young chemist. So I am going to start talking about a topic that you're going to be very uncomfortable with, and I don't really like this stuff either. So it's just something that you need to be aware of, and we are going to acknowledge, and we need to learn because it is a part of our standards, but also because it is really important for you to understand that not all bonds or covalent bonds are done in like these perfect pretty little lines. And so I'm going to basically talk about molecular geometry, and so what it looks like or what the true shape of a molecule is based off certain characteristics that it has. So please be ready to write more notes in class because these notes are pretty brief. I've given you the examples and the names of those examples, but I didn't go into detail. So I will be explaining these in detail in class. I feel like of all of the sections we've learned so far, this may be a little overwhelming and very stressful for some of you. Don't freak out. We will go over it all. We'll spend a good week on all of this information. By the end of this video, you should be able to explain the basis of VSEPR theory, predict the shapes of molecules and polyatomic ions using the VSEPR theory, account for variations in bond angles based on the relative repulsive forces exerted by lone pairs and bonding pairs of electrons, and describe the relationship between molecular geometry and electron domain geometry. So a lot of words there, and you probably have no idea what I just said. Basically, all we're doing is we are looking at specific molecules and their situation and how the electrons are actually going to bend and shape the molecule based off of repulsion. So because remember, electrons are the same force, they're going to have a repulsive nature to them, and so it's going to pull and bring molecules into specific shapes. I'm going to do that. Oops. Well, that's awkward because everything. All right, so let's go ahead and first start talking about the VSEPR theory. But before I do that, I want to make sure that you understand this all coincides with the Lewis electron dot structures. So remember, if you do not know how to do that, if you do not know how to draw a Lewis dot structure, you need to make sure you understand that. You need to make sure you come in for help, get that all acknowledged, because if you don't understand how to do the structure, you will not succeed moving forward in this chapter. Molecular geometry is all based off that Lewis dot structure. So if you can't draw that, you need to be in for help. All right, so another thing, make sure you understand the bonding pairs of electrons and what are lone pairs. So the difference between the two bonding pairs, lone pairs are specific to just one element only of that molecule. So before we start, molecular geometry, you need to know what that is. So molecular geometry is the 3D arrangement of atoms in a molecule. So right now, we have currently been drawing these structures as a two-dimensional structure. They all look like pretty little lines connected, and it's great. We're learning that, and then I'm going to change it up and tell you that it's actually more of a 3D structure. And how this works is that because of the fact that we have lone pairs and we have shared pairs, there's a pooling on the specific bonds. So molecular geometry or shape of a molecule is an important factor, and this not only affects chemical properties of a compound, but also physical properties. So the way they look, the way they melt, solubility, various things like that. And when we go into the lab, we're going to see that melting sugar is a lot different than melting salt, and the properties are a lot different, and this coincides with the shape and what the specific electrons are doing in that particular compound or a molecule. So let's go ahead and just go into VSEPR theory. So before, I keep saying before. Anyways, the valence shell. Remember that the valence shell is the outermost occupied shell of electrons in an atom. So it's where the valence electrons hang out. And these are the electrons that actually do the bonding, and they're involved with the Lewis structures. So there is a nice little theory that revolves around that. It's called the valence shell electron pair repulsion model. So VSEPR, valence shell electron pair repulsion model. And what this is saying, that a molecule will adjust its shape so that the valence electron pairs stay as far apart from each other as possible. And hopefully you're like listening to this and you're thinking, yes, that makes sense. Why would that make sense? Well, based on the fact that negatively charged electrons repel each other. We're dealing with just electrons right now. So that, yes, remember we talked about how a bond works is the attraction between protons and the nucleus, the positively charged nucleus and the electrons. But the repulsion factor is the fact that the electrons in the outermost shell will repel each other. And so this is what causes this three-dimensional shape to happen. And not all of molecules that are formed will shape in the exact same way. It all depends on characteristics that they hold. So there are specific classifications of molecules according to the number of bonding pairs of electrons and the number of non-bonding pairs or lone pairs around the central atom. So for the purpose of VSEPR model, a double or triple bond is no different in terms of repulsion than a single bond. So great, you know how to do a double and triple bond, but in regards to VSEPR, it doesn't really matter. So I'm going to give you a few scenarios, and when I say a few, I mean a lot, and you are going to, or I'm going to help you determine what the shape of that specific scenario would be. And so they're classified based on lone pairs, and remember it's involved with the central atom. So central atom with no lone pairs in comparison to central atom with one or more lone pairs. There are more classifications with one or more lone pairs than with no lone pairs. Oops, it's gone now. All right, I talked a lot in the last slide. Basically what I was trying to say in that last slide was that we are classifying the different shapes that molecules take. There are tons of different molecules, but generally there are specific patterns that we follow in regards to classifying the molecular shape. So I've given you the examples here. There are 6 examples here, and I've given you the name of that molecular compound. So for the sake of trying to keep this as easy as possible, remember some things that generally the first element in a compound or a formula. So here we go. We have BeH2, also known as beryllium hydride. The Be is in the center and it's surrounded by our hydrogens. So 2 hydrogens. This is our first scenario. If you remember from the last video and when I talked about these in class, this is one of those exceptions. You would think that beryllium, because it's a metal, it's going to form an ionic bond, but based off of the fact that it loses 2 electrons, it does not follow that perfect octet rule. So it generally forms molecules. I would say this is one of the most easiest concepts when it comes to molecular geometry, because it's basically what we've learned. So if we remember, again, this does not follow the exact octet rule, but when you create the Lewis structure for beryllium, you're going to have a Be in the middle with 2, not just beryllium, but beryllium hydride. You're going to be in the middle with 2 electrons surrounding it. Again, doesn't follow the octet rule, but I did explain this in the last video on regards to why it doesn't, and I also did in class. Now, this is the Lewis structure for beryllium hydride. And if you notice, again, there's 2 hydrogens on the sides. This is what we call a linear molecule. The reason why it's linear is because these 2 hydrogens here, giving off their bonding pairs and from the beryllium as well, they are going to try and be as far apart as possible. So these 2 hydrogens are going to direct themselves on complete opposite ends of each other as far away. So the beryllium is in the middle and the hydrogens are like as far away as possible as they can be while still holding that bonding structure. So this is known as a linear molecule. The second one that also follows linear geometry is CO2. Again, C is in the middle. Remember, double bonds do not matter. Oops, I have an extra dot in there. There we go. And then over here I have my O. Again, I have an extra dot from the hydrogen that I drew earlier. All right, so that is the Lewis structure for carbon dioxide. This is the second example I'm giving you. Again, remember C is in the middle. It is the first in the formula. And you have 2 O's surrounding it. I'm doing the Lewis structures pretty quickly in this because I'm not focusing on how to do Lewis structures in this video. You should know how to do that. Again, if you don't, you need to come see me. But notice that the oxygens surround themselves to where they're as far away as possible from each other while still holding that bond. So again, these have a linear structure. As we progress on and we create molecules with more than 3 elements, we see that there is a little bit of a change or a little bit of a shape change. So I'm going to go ahead and erase this, and I'm going to talk about the next 2 here. If I can, there, my eraser's already on there. So again, that was linear structure, pretty simple, pretty basic. That's how we've been drawing everything so far. The next example I have is what's known as trigonal planar, or BF3. So again, B is in the middle. My boron is in the middle. And then I have 4 fluorines. So this is known as boron trifluoride. We've been typically drawing it like this. Here's the Lewis structure, you know. Oops. Clicked on something I shouldn't have. I can't really draw. I have a little thing at the bottom there and I can't really draw it well. One thing that you need to also remember is that this also does not follow the octet rule. So boron is it's satisfied without that octet or that 8. So you only have the electrons surrounding all of the fluorines. I didn't complete that octet over there. But this is how you've typically drawn it. Now I'm going to change that up. The geometry of BF3 or boron trifluoride is known as a trigonal planar. The fluorine atoms are positioned at the vertices of an equilateral triangle. So basically what they're doing is the fluorines are creating this 120-degree angle, and this is the farthest away they can be from each other in the same plane, but still not overlapping and not interacting with one another. So I'm going to go ahead and change this Lewis structure I have on here, and I'm going to show you what it truly looks like. So here's boron. Again, that's still in the middle, but it's going to form what looks like more of a triangle shape. So if you notice, it doesn't look super different than what that linear structure I had, but again, all of these fluorines are as far apart from each other as possible. Biggest thing you need to acknowledge is the fact that all 4 atoms, they lie in the same plane, and they are 120 degrees apart. So I know this isn't drawn to scale, but you should know that these are all 120 degrees apart from one another. That is what's known as trigonal planar. And I can tell you, I feel like this video is going to go on for a very, very long time, and we're going to talk about this quite a bit in class. So I am going to briefly go over the different structures for the next 3 examples, but I'm not going to draw them. I will draw them in class. Please don't freak out right now. I know that you're like, I don't understand this. I'm going to have to teach this to myself. I will do this in class. But CH4, also known as methane. This is a compound with C in the middle, surrounded by 4 hydrogens. If you were to draw the Lewis structure, it would look like a perfect little square. This takes on the shape of a tetrahedron. It's a tetrahedral shape. And so basically you're going to have the bonds, they're going to form a 109.5 degree separation from each other. Obviously a lot bigger than that 90 degree. And what's going on is that you're going to have these like different variations of where they point out. And I'm going to, there's a lot here that I'm saying without showing you. So I'm going to draw it. But again, for the other ones, I'm not going to draw. So C is in the middle. You have your H's. Oops, that other H didn't show up. H, and then H. And I know those symbols are really weird, but basically what I'm trying to tell you is that you have a tetrahedron look. It's not just all perfectly hanging out in this nice boxy shape like this one did. So this is what we've typically been drawing. There it is. Okay, sorry. But it doesn't look like this. It actually looks more like this. That's showing that the hydrogens are coming out in a more three-dimensional characteristic instead of that perfect 2-dimensional shape that we've been looking at so far. The other types of shapes, I can't even erase that. The other types of shapes that we have are known as trigonal, bipyramidal, and then octahedral. I'm going to do those in class because I already feel like you're overwhelmed. I can feel your overwhelmedness, and I can feel that this slide is taken forever. All right, so the next scenario we have is when your central atom, so far all we've talked about are the shapes that are involved with the central atom not having any lone pairs surrounding it. Great, I think that's like, okay, that has a shape, that's a molecular geometry. But now what we're going into is central atoms with 1 or more lone pairs. So the molecular geometries of molecules change when the central atom has 1 or more lone pairs surrounding it. So those lone pairs will actually help determine that shape. So the total number of electron pairs, both bonding pairs and lone pairs, leads to what's called the electron domain geometry. So not only do they have what's known as the molecular geometry, they have what's known as electron domain geometry. And this is based off of those bonding pairs and lone pairs coincide or conflicting one another to determine the shape. So we talked about central atoms, or in the last slide we talked about the central atoms that do not have those lone pairs. They have electron domain geometry. They also have molecular geometry, but those electron domain geometries and molecular geometries are the same. And that's for atoms that do not have any lone pairs. When it comes to central atoms that have lone pairs, we then have a difference in electron domain geometry and molecular geometry. And so I'm going to list those off but I'm not going to go and draw these all on here. We are going to be doing some simulations in class, and we're going to be building these models in class. So again, please don't freak out. I'm just introducing this to you, and I don't expect you to understand when you come into class. You should have questions. You should be confused right now. It's brand new stuff. It's thinking in three-dimensional shapes, which can be very hard and difficult for some of us. All right, big thing you need to know is that when you have a total number of electron pairs, let's say you have 3, the number of bonding pairs is 2, and you have 1 lone pair around the central atom. You're going to have a trigonal planar electron domain geometry. Your molecular geometry is what's going to be known as bent, and the example here is O3. When you have 4 total number of electron pairs, 3 of those which are bonding, 1 is a lone pair, you have a tetrahedral trigonal pyramidal molecular geometry. If you have 2 lone pairs with 2 bonding pairs, you are a tetrahedral and you are bent. If you have 1 lone pair, you are with 4 bonding pairs, you are a trigonal pyramidal or a distorted tetrahedron, also known as a seesaw. If you have 2 lone pairs, 3 of those are bonding. You have 3 bonding pairs, 2 lone pairs. That's known as a T-shape or with the electron domain geometry of trigonal pyramidal. If you have a number of bonding pairs, which is 2, and a number of lone pairs, which is 3, like in the example of CIF3, you have trigonal pyramidal and linear. I might have read that wrong, but we'll get to that in class. Number of bonding pairs is 5, and the number of lone pairs is 1. You have an octahedral square pyramidal, example BRF5. And then finally, a number of bonding pairs, which is 4. Number of lone pairs, 2. You have an octahedral square planar. There's a lot there. And I can feel that you are very uncomfortable right now. But it's okay. Again, we are going to go through these in class. We're going to go through this very slowly. I'm going to show you some tables in class that hopefully this makes more sense. I'll give you those examples. I'll draw these in class with you. And hopefully we'll start to click and make those patterns. Because basically all it is a pattern. You acknowledge how many bonding pairs you have. Acknowledge how many lone pairs you have. And then you put the electron domain geometry and molecular geometry with that. So a lot of it is a memorization. And practicing, memorization and practicing. So we're going to continue to do that in class. Don't worry. If you have any questions, please don't feel afraid to ask me on Edpuzzle. Do not be afraid to tell me you do not understand. It's totally fine. It took me so long to try and even figure these out and to get these right in geometry, and still it gives me stress just looking at the shapes. Again, remember the VSEPR theory. We're just looking at how electrons interact with each other and the fact that they don't want to be close to one another. So that repulsive force is what pushes their shapes. It makes them more of a three-dimensional shape rather than that linear shape that we have been acknowledging when we do these Lewis dot structures. All right. Again, if you have any questions, please ask me on Edpuzzle. I know this was very quick, very brief. Good luck.